Good day, everyone. So, in today's class, we'll be diving into the topic thermal expansion and conductivity. At the end of this lesson, we'll be able to know how materials respond to heat from microscopic particle motion to real world engineering solution. So, let's dive into this. Now, firstly, we are going to be looking at what thermal expansion is about. Now, when we talk about the word thermal simply means heat. Okay, so when we now say thermal expansion, it means expansion that occur as a result of heat. Okay, so sometimes substances expand when they are exposed to heat, and such expansion is called what? Thermal expansion. And when they expand, they can either expand in one direction, which is called the linear. The expansion can also come in form of 2D dimension, which is called the area expansion, and it can come in 3D dimension, which is called the volume dimension. Okay, sometimes we call the area uh, expansion, we call it superficial expansion, while we call it volume expansion, we call it sometimes cubical expansion. So those are the three ways that expansion can occur when it is involved, either in linear way, which is 1D, or in area, sometimes called superficial, which is 2D, or in volume form, which is sometimes called cubical, which is 3D. Okay, so one after the other, we're going to consider each of these type of expansion. The first one is linear expansion. When you subject a solid substance, especially maybe a metal, to heat, they tend to expand linearly. That means in one dimension. So, what is the definition of linear expansion? In terms of the concept, we call it linear expansivity, and we use this Greek symbol called alpha to represent it. This symbol here is called alpha symbol, so it represents linear expansivity. Some textbooks call it the coefficient of linear expansivity. It's still the same thing. Either it is called linear expansivity or coefficient of linear expansivity. For whatever case, this symbol remains the same. For linear expansivity, we use this symbol. So what is linear expansivity? It is a change in length per unit change in temperature. Okay, the change in length per unit change in temperature. Okay, look at the formula. Yes, my formula is going to be delta L over L delta T. Delta L there means change. The symbol, that triangle symbol means change. So change in length over L. L is the original length. Then multiply by change in temperature. Delta T means change in temperature. Okay, the symbol there means change. So if you cross multiply this now, we'll be having delta L to be equal to alpha delta T. So, and the unit of linear expansivity is per Kelvin. That's K per minus 1 per Kelvin. All right. So we've said it before that the delta T may change in temperature or temperature change. All right. So aside from linear expansivity, we have the area expansivity too. We use beta symbol to represent area expansivity, as you can see here. So its own definition is that it's change in area per unit change in temperature. Okay, the linear one is change in length per unit length temperature, but for area expansivity, it is change in area per unit change in temperature. Okay, so wherever we see L, we put A. That's just the difference. The previous one we said that L is equal to alpha L delta T. But for area now, wherever we see L, we put A. It's going to be delta A equal to, instead of having alpha now, we have beta because we are dealing with area expansivity. Beta A delta T. All right, that's the difference now. The unit of area expansivity, which is beta, is also per Kelvin, just like linear expansivity. So they have the same unit. Area expansivity or coefficient of area expansivity have the same unit as that of linear expansivity. That is per Kelvin. All right. The third type of expansion is called the volume expansion. or the volume expansivity. So we use gamma to represent this. It's not Y. This symbol is not Y, it's gamma symbol. So what is the volume expansivity is defined as the change in volume per unit change in temperature. Remember I said sometimes we call this volume expansivity cubical expansivity, while we call the area one, we call the area superficial expansivity, and then we call the volume cubical expansivity. So volume expansivity is represented with the Greek symbol gamma, and it's a change in volume per any change in temperature. So wherever we see A, we put V. For area it is what A. So delta V now equal to, instead of putting beta, gamma V delta T. That's the formula generally to determine either change in temperature of that substance or the change in volume or the original volume. Okay, its unit also is per Kelvin. So for cubical, it is per Kelvin. For superficial, it is per Kelvin. For linear, per Kelvin, the unit. All right. So then, what's the relationship between these three types of expansion for linear, area, and volume? Now, of course, linear is one dimension, area is two dimensions. So area expansivity is equal to 2 times linear expansivity, while volume expansivity is 3 times linear expansivity. Okay, that's why it is 3 dimension. So it is when you multiply 3 by linear expansivity, you get volume. When you multiply 2 by linear expansivity, you get area. That's how the three of them are related by formula. Okay. Now, what is the consequence of expansion? We have seen that there are 3 types of expansion, but does expansion have consequence? Yes, it does. Imagine a substance just expanding. That effect. Now, the bridges that we see on the road, okay, and buildings. Imagine bridge expanding. When the bridge is expanding, definitely you should expect that there will be demarcation with time, and it could cause accident. Okay, so the this is the consequence of expansion here. It's not application here now. So in bridges, it's consequence. Consequence is the negative impact it has. Okay, so expansion of bridge is the negative impact of expansion. Even building too can collapse because of expansion. Overhead cables too. Overhead cables with time expand, and that is why you see them sagging. You see these cables that are here now, with time you see them, they will have beginning to have a curve shape because they have expanded. This also consequence, the consequence of expansion. Okay, so the heat causes the sagging of the wire. Okay, and then they begin to, instead of them to be straightened, you see the wire being curved. Now railway line. Now railway line is more of application. This is an example of railway line. Now you could see. Have you ever wondered why you have spaces between these lines, these metal lines of the rail? That's because space has been created for the expansion. Okay, so this is an application of expansion now, and it's not a consequence because of the space now. During the daytime, when the sun is having is very hot, this metal expand, and the space there is what they occupy. So with that, the train that is passing, when the tire will not be locked due to the expansion. Okay. Now in liquid too, you can see that liquid can expand to become gas because of heat. Okay, so expansion of liquid is also an application because when you are going to boil your water, we're going to boil your water, there must be an expansion before water can boil. All right. So, but there is one aspect of expansion of water that we call anomalous behavior of water. Okay. Now, when you are boiling, when you are heating up water from 0 to 4 degrees Celsius, water does not expand. Water will rather be contracting from 0 to 4 degrees Celsius. Then from 4 degrees Celsius upward, it begins to expand. This phenomenon is referred to as anomalous behavior of water. The point where water is supposed to expand and is contracting, that's the anomalous part between 0 to 4 degrees Celsius. Okay? Now, what we call another application of it is called bimetallic strip. Okay, bimetallic strip simply means two metals that are combined together. Okay, combination of two metals, for example, steel and brass combined together. Okay, and when they are combined together and you subject them to heat, the one with the lower expansivity will bend inward. Let me give you an example of what I'm saying now. Okay, let me give you a diagram of this. Let's say now you have something like this. This is the first diagram here. Let's say this first diagram is let's call this one steel, and then let me now bond it with another metal. Okay, so let's call the up one brass. Let's say this one is brass and this one is steel. Okay, this is how bimetallic steel look like. You just have two metals, okay, combined together. Now when they are subjected to heat, if it is steel that has the lower expansivity, then the bending will be upward like this. All right, it will be upward this way, so that steel will not be the one that is down. Okay, so this the down part is steel because it has a lower expansivity. But if it is steel that has higher one, then it will bend the other way. That is it. And where do we apply these bimetallic strips? Bimetallic strips are applicable in thermostats. Thermostats are devices that help us to regulate our temperature. Okay, it controls heating system, but majorly to regulate temperature. We can find this thermostat in our pressing iron. You know, when you are using your pressing iron to iron your clothes, you see that sometimes the light will turn off and automatically it come up. It is the thermostat that is at play there, because what is happening there is that these bimetallic strips, when it gets too hot, it bends. Initially it is straightened, but when it gets too hot in the thermostat, it bends, and when it bends, it disconnects from the contact, from the electrical contact. And when it disconnects, it begins to cool down. And when it cools down again, it reconnect again, and when it reconnect again, it begin to what bend. So that's how thermostat work, to regulate temperature. Then we can also apply it in thermal overload protection. This bimetallic will also work there. It works in fire sprinklers too. The same way it's operating in thermostat, that's how it works in every other one here. In automotive, it works in cookware safety, clock and watches, electrical contact, expansion joint. These are the areas where we can see these bimetallic strips in play. Okay, so having said that, let's look at some other concept called, we have looked at thermal expansion. Now we have what we call thermal conductivity, solar energy, and black body radiation. Okay, we use the symbol K to represent thermal conductivity. Now, thermal conductivity measures how well a material conduct heat. Okay, whether it can conduct heat at uh, it can conduct heat fast or low. Okay, so you can either it has high conductivity or it has low conductivity. Okay, and the material that has low conductivity is known as insulator. The one that has high conductivity, it's called conductor. Okay, now there are panels too. There are panels that convert sunlight energy to electrical energy. We call them solar panel or photovoltaic panels. So what they do is that they trap the energy of the sun, the energy of the sun, and convert it into electrical energy. Okay, and there's a part that we call the black body radiation. Now, ordinarily, every black object is meant to absorb radiation. Why white object or bright objects, they reflect it. So be it known that it has been verified rather that black objects absorb it. Okay, they absorb it a lot, meaning that they can also generate it. When they can absorb it, they also will generate it, because once something can absorb it, can also the heat that has been absorbed can also generate it. That's why we call it black body radiation. They only radiate heat that has been absorbed. So, having said this, let us look at one or two questions on this topic, and then we call it a day. Look at this question here. It says, a steel plug has a diameter of 5 centimeters at 30 degrees Celsius. At what temperature will it fit exactly into a hole of constant diameter 4.997 centimeter? Coefficient of linear expansion of steel is 11 times 10 to the power 11 times 10 to the power, this should be power, to the power 6 degree, uh, degree per degree Celsius. Okay, take note of that. Option A, we have 27.3 degrees Celsius. B, we have minus 27.3 degrees Celsius. C, we have minus 2.7 degrees Celsius. D, we have 7.32 degrees Celsius. And E, we have 2.7 degrees Celsius. Okay, now that we've seen this question, let us take it one at a time. Now, so let's take it again. Let's see the question again. It said a steel plug has a diameter of 5 centimeter. So that's the original diameter of that steel. Okay, so let's call that L1, that original length is equal to 5 centimeter. And okay, this is 5 centimeter. It has this length at the temperature. So this is our T1. Our T1 is 30 degrees Celsius. Okay. At what temperature will it fit? So we are looking for T2 now. So the temperature is unknown. At what temperature will it fit exactly into a hole of constant diameter 4. So we want it to fit into this hole. That means the final length now. So we are giving L2 to be equal to 4.997 centimeter, right? So, and we are given coefficient of linear expansion means alpha is equal to 1 times 10 raised to power 6, okay, per degree Celsius, okay, per degree Celsius. So that will be to power minus degree Celsius. So we are looking for T2. So the best formula to use is, okay, let's mark it our screen. So we have the formula to use is linear expansivity equals to L2 minus L1 over L1, then into bracket T2 minus T1. Now, this formula is the same thing as writing that change in L over L1, change in temperature. It's the same thing. This delta means change, okay, and change means final minus initial. So we have this now, so we now have to return our value. Our L2 is given to be 4.9, so 4.997 minus L1 is 5, okay, over L1 is still 5, right? Then we have open bracket. Our T2 is unknown, so that's T2 minus our T1 is 30. Okay, that's it. So moving forward, let's now calculate it. So this alpha, no, we're calculating alpha, and then our alpha is given. Remember that our alpha is given to be 11. So we have 11 times 10 to power 6 equals to, now equals to the value of 4.997 minus 5. So 4.997 minus 5. So that will give us 0.003, right? So we are having, so at the numerator here we have 0.003 minus, okay, over 5 into bracket T2 minus 30 as something from here. Okay, now when we cross multiply now, when we cross multiply this, when we multiply 5 by this, so we're going to be having 55 times 10 to the power 6, okay, to bracket T2 minus 30 Okay, then everything equal to 0.003. Right? Now, still moving on, then we need to divide both sides by 55 times 10 to the power 6. So that means T2 now, when we do that, T2 minus T2 will be given us minus 0.003 over 55 times 10 to the power 6. Alright? And then that will be equal to, now let's get a calculator to do this. Now using our calculator, we have 0.003. So we have 0.003 to be divided by. So if you multiply 55 by 1 million, so we'll be having divided by 550. Okay, so we have that will be divided by 5,500,000. Okay, divided by 5,500,000. That will be equal to, okay, 5.45. Okay, 5.45. So all of this give us 5.45. Okay, so wait, let's do this. Okay, this is 50, it's supposed to be 55 million. Not 55 million. Let's do it again. That's a mistake. So we have 0.003 divided by 55 million. Okay, 55 million. So that's giving us 5.45 approximately. So at the right hand side we have minus 5.45. Now that's on the left hand we have T2 minus 30. Now T2 will now be equal to minus 5.45 plus 30, or we say 30 minus 5.45. Okay, so 30 minus 5.45. So that will be giving us 24. That will be giving us 24.55. Okay, so that will be giving us 24.5. We have it here as a final answer. 24.55 degrees Celsius. Okay, so that's our final answer, and that's the final temperature. But if you come here, you will not likely see the option because there's an error in the coefficient of linear expansion. Yeah, this value, there's an error there. Okay, but let's just work with what we have. Whatever error there, let's work with that error. Our answer will give us 24.55 degrees Celsius. All right, so we are going to be doing the cutting here. I hope you have been able to understand what linear expansion is, cubic expansion is, and superficial expansion is, as well as conductivity. So thank you for listening and have a wonderful day. Bye for now.